Hi everyone, and welcome to this presentation. We are going to examine the Contiki operating system, and we shall provide some coverage of the core concepts required to understand how it behaves, especially in regards to events, processes, and what is known as protothreads. Starting with an introduction, Contiki is an operating system for the Internet of Things. The origins of Contiki goes back to the dreams of its creator Adam Dunkels, who works for the Swedish Institute of Computer Science. Today, Contiki is deployed within a number of different industries for both commercial and non-commercial usage. Applications vary widely from including automobiles, airplanes, satellites, container tracking, and television production equipment, just to name a few. An overview of Contiki. Contiki operating system falls within the category of event-driven systems. This means that the applications executing on the OS are triggered by events. An application consists of a process, which is also considered an event handler. Anytime an event is destined for the process is scheduled and the event is delivered to the process in the form of activating its event handler. The event handler parameters allow for the event, along with any data, to be passed to the handler so that it can be examined and acted upon. Before we dig into the concept of protothreads, there are a few concepts that need to be understood. We need to talk about events and about processes first, and then we will mention and talk in detail about protothreads and process control. These four elements are really important to understand how Contiki operating system operates. Let's start with events. Events are at the heart of Contiki operating system. They play an important role in the proper functioning and interaction between the kernel, applications, and drivers within the system. Each application essentially is one process with a main entry point corresponding to an event handler. All interactions are based on either shared global data or event communication. There are different ways of classifying events. Namely, there are two. The first type is based or determined by the destination of the event. Events can have either a single process recipient, that is a single receiver event, or all processes. That's what's known as the broadcast event. The second method by which an event is classified is determined based on whether the event is a synchronous event or an asynchronous event, thus distinguishing the kind of event being sent. Asynchronous events are queued in the kernel's event queue and delivered when the OS schedules that event to be delivered. For asynchronous events, the kernel must keep enough information so that it can later schedule a process to receive the event. Therefore, for each event in the event queue, 3 pieces of information are maintained as specified within the kernel source event data structure. And these fields include the EV, that stands for the event number, the data, which is a pointer to the data associated with the event, and the field P, which is simply a pointer to process structure receiver. Now let's talk about processes. The kernel process module is found in the file Process.C. It is the heart of the operating system. It contains a number of APIs for manipulating processes, events, and also for scheduling. There are 2 main data objects that exist here, the process list and the FIFO, or the FIFO, asynchronous event queue. Let's talk about the process structure in Contiki. For all active processes in the system, Contiki must keep track of them so that they can be scheduled when events arrive, restore context when they are blocked, and know what state they are in at any time. And second, for each process in the process list, 6 pieces of information are kept, as specified in the table below. Within the kernel's process structure, you can see that we have the next, which is a pointer to the next process in the process list. We have a name to the process, a thread, which is a pointer to the protothread event handler. We have a PT, which is a protothread corresponding to a process. And we will talk about this in detail as we look into the code of our Hello World example. We also have the state, which designates the process state, could be none, could be running or called. And finally, the needs poll, which is a flag requesting that process check for data. And finally, we need to know that code in Contiki can run in one of 2 execution contexts, a cooperative or a preemptive. Code running in the cooperative execution context is run sequentially with respect to other code in the cooperative context. Cooperative code must run to completion before other cooperatively scheduled code can run. Preemptive code, on the other hand, may stop the cooperative code at any time. When a preemptive code stops the cooperative code will not be resumed until the preemptive code has completed. The concept of Contiki's 2 scheduling contexts could get a little bit tricky, but I just wanted to mention it for the sake of completion of this demonstration. Now, let's move on to talk about protothreads. And that's the heart of this presentation. A protothread is a stackless thread. It makes it great for use in small footprint systems, such as those operating systems for embedded systems. Particularly in Contiki, this works great because the memory is not wasted on multiple stacks and that are usually only partially used. This means that protothreads are also well suited for the types of applications that Contiki is targeting. A protothread consists of 2 main elements, an event handler and a local continuation. The event handler is the one associated with the process. The location continuation is used to save and restore the context when a blocking protothread API is involved or invoked. It is a snapshot of the current state of the process. The difference between a local continuation and a more general continuation is that with local continuation, the call history and values of local variables are not preserved. The main benefit for using protothreads is to provide a conditional blocking inside a process event handler. Traditionally, event handlers cannot block as they implement run-to-completion mechanism. If an event handler did not return, it would prevent the scheduling of other processes. However, when using protothreads, they allow blocking operations within an event handler through the use of special protothread blocking operations. Some state machines are normally found there within an event-based application that can be eliminated. More on protothreads. Protothread APIs are implemented as macros within Contiki. These macros, when expanded, actually expose the implementation of protothreads, especially the inner workings of the local continuation. And this is something that we will look at as we look into the code. A particular implementation of a local continuation, a switch statement, in combination with the associated cases, actually save and restores the context of the thread. Hidden return statements combined with a switch statement is used to provide an illusion of blocking at the application level. Now, a side-by-side comparison of the code implementation shows that the actual size is significantly decreased through the use of protothreads. The protothread example, which we will look at, shows that normal sequential blocking operations can be implemented in a much simpler manner. The result is less application code, clearer implementations, and blocking operations and event infinite loops. Let's look at the structure of protothreads and how it works. First, you start with a process declaration. Every process in the application should be defined via the process macro before using it. Then we have an AutoStart list, which is a list of processes that needed to be automatically started when the module is booted. This list is managed by the AutoStart_Processes macro, and we will look into this in detail. And third, we need to have an event handler. Each process in the module has a body which functions as an event handler. The body, which starts with the process_thread macro, contains 3 steps. First, initialization, in which the resources are allocated and variables are initialized. Then we have an infinite loop, which is waiting and processing of events take place. And finally, the last step, resource deallocation. This is where we release the resources at the end of the process thread. It's very important that we talk about process control even from a high level. Processes, in general, can start and stop other processes, as well as they can stop themselves, and also they can post events. Since events are a normal part of inter-process communication on Contiki, these APIs are used frequently in general applications. The figure that we're looking at only identifies the most common APIs that are used for process and event handling as well as scheduling. The Contiki operating system is used to start processes during the boot sequence. Processes related to the I/O or the kernel services are, as well as general application processes, are defined to the kernel as needed to be automatically started when the operating system is booted. These types of services could be such things as networking stacks and event timers. Now I want to start looking at our HelloWorld.C. This is the example that we will be looking at, and we'll try to trace the code back and forth between the libraries of Contiki and the different macros within. So looking at the HelloWorld.C, we can see that the first include Contiki.H would really trigger us and intrigue us to go into the Contiki.H file. And then we would realize that Contiki.H provides access to the Contiki operating system process and protothread macros. It appears that the Contiki operating system, or the Contiki OS, AutoStart programmer defined processes and schedules these processes using local continuation. These scheduled processes will become events in an event-driven system. The header files contained in Contiki.H access these resources, obviously. So looking at this Contiki.H, it provides access to the Contiki OS thread and protothread macro definitions, including the process, AutoStart, timer, process init, and the clock. And now looking back at the Hello World, let's move on to the next statement. Actually, I'm skipping process Hello World for now because we will go in a different sequence. Let's talk about the AutoStart processes. This is really important because this is what starts everything. Contiki provides a mechanism whereby processes can be automatically started either when the system is booted or when a module that contains the process is loaded. Here, when we see the AutoStart_processes, we are going to find it inside of the core/system/AutoStart.H. This is the file. And this mechanism implemented by the AutoStart module. The process of the AutoStart mechanism is to provide a way that the developer of a module can inform the system about what active processes the module contains. Auto-started processes are kept on a list that is usually by the AutoStart module to start the processes. The processes are started in the order they appear on the list. It's worth mentioning that processes always run in cooperative mode, whereas interrupts run in preemptive modes. Now, looking again at this document that we have here, the AutoStart.H, This is the process hello world process. When a module is loaded, the module loader finds the list of AutoStart processes and starts these processes after the module has been loaded into the executable memory. When the module is to be unloaded, the module loader uses the same process list to kill the processes that were started as part of the module loading process. In Contiki, the AutoStart mechanism is the most common way through which user processes are started. Now, going back to our HelloWorld.C, we're going to move on to the statement here that is process HelloWorld_process, Hello World process. This, we were able to trace it back basically to the file core/system/process.H. This is a declaration of the process hello world process, and it contains the process control block. Now, here's where we really need to understand what this is. A Contiki process consists of two parts: a process control block, that's what we're looking at, and a process thread. The process control block, which is stored in RAM, contains runtime information about the process, such as the name of the process, the state of the process, and a pointer to the process thread of the process. The process thread is the code of the process and is stored in the ROM. This is an example of the process control block, which is process hello_world_process, hello world process. It's a lightweight in that sense. It requires only a couple of bytes of memory. The first field in the process control block next points to the next process control block in the linked list of active processes. The name field points to the textual name of a process, and the thread field is a function pointer that points to the process thread of the processes. And finally, the PT field holds the state of the protothread in the process thread. Now, looking at this Process.H and looking at how the process is, as you can see, is defined, it is as you can see, there is a slash at the end of the defined process name string name. This slash, basically in the C language, defines what macro expansion is, and this is a way of expanding your macro and its definition. So process really expands itself through the use of a process called process thread, as you can see here. And looking at process thread, which is right here in the third statement, a process thread contains the code of the process. The process thread is a single protothread that is invoked from the process scheduler. A protothread is a way to structure code in a way that allows the system to run other activities when the code is waiting for something to happen. The concept of protothreads was developed within the context of Contiki, but the concept is not a Contiki specific, and protothreads are used in many other systems as well. Let's look back at Process.H and let's trace here the process thread hello world. It defines the body protothread of the process hello world process. And you can see that there is something here called PT thread. The PT thread is then takes the argument from the process thread and declares the protothread. What follows between process begin and process end is single protothread that will be invoked by the process scheduler via local continuation. Now, Contiki processes implement their own version of protothreads that allow processes to wait for incoming events. The protothread statements used in Contiki processes are therefore slightly different than the pure protothread statements. Some process-specific protothread macros that are used in Contiki include the process begin and process end, the process_exit, the process wait event, and others. Moving on, I would like to talk about the process begin as part of the PT thread. So you can find the PT thread Hello World if you actually go into the process _H, and this is where you can really see the PT underscore thread. It's invoked by process underscore thread, which declares the protothread hello world process, and the PT thread utilizes local continuation. Here the LC resume is invoked by the PT begin, and we can find that the LC macros, including the LC init, LC resume, LC set, and the LC end, defined within the LC switch.h. This is noteworthy since we understand local continuations because as they implement protothreads and capture the function state. Local continuations form the basis for implementing protothreads. A local continuation can be set in a specific function to capture the state of the function. After a local continuation has been set, it can be resumed in order to restore the state of the function at the point where the local continuation was set. Our final comments on the Hello World, as an example, it's a basic protothread created using Contiki's thread and PT thread and the protothread macros to create and schedule events. The Hello World process, in our opinion, does not use a timer, but instead runs to completion using the Contiki operating system built-in local continuations. That concludes this presentation. Hope you enjoyed it. Have a great day.